Good morning, AP Chemistry fans. Thanks for joining us for another live lesson in AP Chemistry. This is Mr. Byrne coming at you from outside Chicago. I teach at Glenbard West High School, and I know there's a lot of Hilltoppers out there that are taking part in these lessons throughout the past couple of days and weeks. Today is Wednesday, April 8th, 2020, and we're gonna, I think, finish up our conversation of Unit 3 on intermolecular forces and properties. We started this by talking about gases, then we talked about solutions yesterday, and we're gonna talk a little bit more about atoms and molecules and do another great lab experiment today, talk about one of the classics that is important for you to have an experience with, okay? So some great stuff planned for you today. Quick reminder to make sure you're checking apcentral.collegeboard.org for all the latest updates. Here's our testing date, Thursday, May 14th. We have a big star on the calendar for that day. Here in Chicago, we're in Central Time, so we'll be taking it at 1 o'clock. Remember, we all will be taking the same free response test at the same time. So these times are local times. So you would just want to make sure that you are aware of when your local time is associated with each of these. The alternative test is something you're going to want to talk to your teacher about, excuse me. Just make sure if you are not able to make the main test, you'll talk to your teacher or an administrator at your school about getting your testing date switched to one of these days. Our format that we went over yesterday, but just to repeat, remember there will be 2 questions that you'll have a total of 45 minutes to look at. We have 25 minutes to read and respond to the first question. That gets us to 30 minutes. Once you submit that first question, you'll be given the second question, but you will not have time to go back. You'll have 15 minutes to read and respond to question number 2, and then another 5 minutes to respond. Okay, or I'm sorry, to upload your response. We're still waiting on some more information on exactly how that will be distributed to us. And as soon as we have that, Mr. Fairbar and I will share that with you. But what we do know is that the format of the questions that we've been giving you for homework would fit really nicely into each of those kinds of questions. And then one of the reasons why we're being really clear to talk to you about the skills that are necessary to be successful in AP Chemistry is because we know that the questions will give you some sort of a system, some data, so that you can shine in your ability to explain the phenomenon using models, theories, and representations. You're going to be able to draw conclusions from the experimental results, to identify and explain procedures that are aligned to a question. You'll analyze a system with quantitative reasoning. So we'll do some numbers. We're going to look at sources of error. I don't want to forget that one. I gave you an experience of that today. And then we're going to support claims with evidence and reasoning. So all of these skills are things that are important in all of our science classes, and you'll have a lot of opportunity to talk about those today. So let's get into our lesson overview for today. We will review our homework problems from yesterday. Then we will be looking at some pretty heady stuff in these 2 topics, spectroscopy and the electromagnetic spectrum, the photoelectric effect. I'm going to apologize already to our physics teachers out there and our physics buffs. If this is something that you're really excited about, you should absolutely make sure that you register for physics next year or as some class in the future. Do some more reading on this. For time, I had to condense this into 45 minutes on all 3 of these topics. We certainly could spend more than an hour on probably each one of them. So we're going to go through exactly what we need to know to be successful on our exam and do some little background so it makes sense to us. At any point, I'm speaking too fast or you want to take a breather, feel free to stop. Make sure you have a pencil and a paper next to you to be able to take some notes and maybe to do some of the practice problems as we're going through them. Okay, so let's get to our warm-up, which is our review of our homework problems from yesterday. We were looking at a free response question from 2017 on paper chromatography. We had 3 pure dyes. Okay, so since we were given to this test was in pencil and paper, of course, we didn't have colors here. So you may want to go back and review the version of this that I gave you yesterday where we had 3 different colors. Okay, this says that these are pure dyes. And so in this case, we didn't necessarily have mixtures. We're just going to have, we're going to do a comparison of what's happening to each of the 3 dyes that are here. So there'd be a difference between what we did yesterday and what we did today, but the same principles are going to apply, and that you have a non-polar solvent that is going to travel through the paper to what is identified over here as the solvent front. Okay, and so we talked about the stationary phase and the mobile phase. Those are words that would be nice for you to know, nice for you to remember. But the fundamental principle here is that we have two chromatography chambers. We have three knowns that are going to be left in here. The knowns will distribute themselves like this. The unknown will travel up the paper like this. We are aware of where the origin is. Two other important pieces of information that this problem gives us: that the chromatography paper is a polar material, and that the solvent is non-polar. Okay, so you can see how we're really building on a lot of the themes, a lot of the ideas that we've been talking about over the each of these lessons throughout, kind of a mini review of the entire year. So remembering what a polar or a non-polar material is, how that would affect itself in a non-polar or in a solvent like this is an important idea for maybe you to take a second to stop, review, and go back and look at the previous lessons on that. So our first question asks, which dye, A, B, or C, is the least polar? And we're going to want to identify our answer in terms of, or justify our answer in terms of the interactions between the dyes and the solvent, or between the dyes and the paper. So I'm going to just zero in on the data that we had here, or the diagram that we had here. And I want to remember that I have to identify that we have a non-polar solvent. So when we're looking at the three dyes over here and we see how they traveled up the chromatography paper, we know that the non-polar solvent traveled from here all the way up to the top. And so what we want to consider is which of these three, A, B, or C, is the least polar. Sometimes I like to think about it as which is the most non-polar, which is going to be most attracted to this solvent, right? So the one that's attracted to the solvent most would be dye C. It travels the furthest with this nonpolar solvent as it travels up the paper. Dye B was not as attracted to the nonpolar solvent, or was more attracted to the paper, which we were told was polar, and so it didn't travel as far up the paper. So our good response here would be dye C is the least polar. We're going to be really clear on what our answer is. This is because it traveled the farthest with a nonpolar solvent. A nonpolar dye is more strongly attracted to a nonpolar solvent. The nonpolar dye is least strongly retained by the polar paper. Okay, so any that you would definitely need to include both of these sentences in the scoring guidelines. Either of these two sentences, either saying that the nonpolar dye is more strongly attracted to the nonpolar solvent or least strongly retained by the paper, was acceptable, but you did need to identify clearly what the dye is and then give a clear explanation of why. Okay. Our second question asks us which dye is present in the unknown sample. So we're told that this unknown matches up with one of these guys over here. And you can see that because the solvent front did not travel as far, this unknown did not travel as far as well. We can suggest a couple of different reasons why this solvent front did not travel as far. Perhaps it was left in the solvent for a shorter amount of time. A couple other reasons. I would suspect for this one, they wanted to make it interesting for us, so we couldn't just draw a line across and match it up. If we drew a line across and match it up, we would be left with something that's right in between. And so we want to have more of a quantitative way of analyzing what's happening in the unknown and comparing that to what's happening in each of our knowns, dye A, B, and C. And that's where we would come into our measurements of the distance that the unknown dye traveled as compared to the distance that the solvent front travel. And what we call that is the retention factor, or R sub F. And here, even without a exact number, without a ruler in front of me, it seems pretty reasonable that this is pretty close to 0.5. And so I would suggest that we would, let's estimate that number right now. 0.5 doesn't have units. It would be distances that would cancel each other out, right? So it's just a straight up number. We're going to estimate it for right now and see if that helps us to get to a clear answer compared to dye A, B, and C. And if we need to get more specific with it, then we would get a ruler out or something like that. So I'm just going to go from right to left on our known dyes, and I would look at dye C. Okay, and this to me, I would estimate at about 0.75. It's clearly significantly more than 0.5 to me, and drawing up my arrows like this makes that pretty clear. The next one over, dye B, I would estimate as about 0.25, so clearly less than half. And I hope you can see where this is going. The dye A looks very clearly the ratio of the distance that dye A traveled as compared to the distance that the solvent front traveled is very similar to what our unknown did. And so a really good explanation for this would include two pieces of information. First, that dye A is present. So we've correctly identified what is the unknown. And then here are the two different ways that the scoring guidelines justify the answer. The unknown sample moves to a position that is midway between the origin and the solvent front, and so does dye A, right? So that's a little more qualitative, not quite, excuse me, as quantitative, saying the same thing as we've said, but I like that second explanation. Dye A has a retention factor that is close to 0.5 on the chromatogram with the 3 dyes, and the unknown also has a retention factor close to 0.5. So I would have gone, I'm comfortable with that second one a little bit more, but we needed to have some clear justification that is there. And it would have to be in terms of the relationship between the distance traveled from the origin by the unknown and the solvent front. You wouldn't want to say something like, oh, this would keep traveling up, and so this dye would keep coming up, and then it would match up with dye A or something like that. That would not be an acceptable answer here. We want to have something that's a little bit more in line with what we do, what we know happens with that retention factor. Okay, so there you go for our first exam or warm-up question. Our second one had to do with aspirin that's dissolved in enough water to produce 200 milliliters of solution. So what's the molarity of aspirin in 50 milliliters of this solution? So we're going to handle the first part first. Let's look at the fact that we know molarity is equal to moles of solute over liters of solution. We reviewed that yesterday. So our moles of solute are 360 360 grams. I made a mistake there. Look, I just checked on that. So we're gonna do some quick math in our heads, and let's see if we can. We're gonna edit this live as we're going through here, guys. And so we're gonna have 0.002 moles of our solution, because we're going to convert that milligrams into grams right there. When we divide it by 180 grams, it gives us 0.002. That's going to change this answer up here to 0.002, right? And so I'm going to move my decimal point over. Look at this, guys. People are going to be talking about this, that we're changing our answers live as we go through here, okay? So I will go back and we'll get a note out to you guys to make sure that I did that correctly. Sorry about that. So we've got 0.02 moles. We're going to fill that in up here, and we get a 0.010 molar solution of aspirin in that original solution, right? Now, the question, though, asks, what's the molarity of aspirin in a 50 milliliter sample of the solution? And that sounds like it's a trick question. It sounds like we're going to have to do some more calculations. But what we want to remember here is we were just pouring out 50 milliliters of this 200 milliliter solution that was already there. So whatever the molarity of this solution is, the molarity of the 50 milliliter solution stays the same, right? It would be as if we had a beaker with 200 milliliters in it. When I pour 50 milliliters of that out, the molarity does not change. The molarity stays the same. The molarity would only change if I added water to it, or if I evaporated some water out of it. But because the way that's written, I read this as we're just pouring out 50 milliliters of the same solution. We're going to say that our final solution here is 0.010 molar. That's the molarity of the aspirin in the solution. Okay, we're going to jump through that slide real quick for my mistake. I apologize for that. Okay, here's the mass. This looks very similar to what we did before. I just wanted you to have another experiment. Oh, I'm sorry, what we did as one of the practice problems during class yesterday. I wanted you to have an experience of this pentahydrate, copper 2 sulfate pentahydrate. So we know that moles are equal to molarity times liters of solution. So we're going to end up with 0.025 moles of CuSO4 is what we're looking for, but we need to multiply that by the molar mass of copper 2 sulfate pentahydrate, right? So we're going to make sure that we include all of this in here, and we should get to something like 6.24 grams. All right, that was exciting, making some changes on the fly, but hope that we got the right answer out there to you. Let us know if we made a quick mistake there. But let's go into our discussion of our 3 topics and a couple of guided practice problems. We'll talk about the spectrum, talk about its photoelectric effect, and then what's sometimes referred to as Beer's Law or the Beer-Lambert Law. Both of them are pretty familiar, are the same. We're looking at some spectroscopy and the electromagnetic spectrum. We're explaining chemical properties here, okay? We're explaining phenomena. We go back to what we will have to do on the AP test. Given some theories, models, representations, so we want to make sure that we understand what's happening in this phenomena as a way to explain what's happening in the model. Okay, so one of my favorite days in chemistry class is when we get to get these glass tubes out, and what's happening here in these glass tubes, I hope that you have an experience of something similar to this. It looks a lot like a neon light, right? But instead of being neon on the inside of this, this is hydrogen gas, and a current is run through it. So this is put in an apparatus that's plugged into the wall. It would look to you, if you were in a classroom, very much like just a kind of a straight, boring neon light that doesn't have any shapes or letters or anything in it. But what your teacher would probably do would be either to give you some glasses that have prisms in them, or give you another apparatus that will help you to spread out this light, put it through some side of a prism. And what you would see on the side of this is these really cool bands, these cool bands of light that are at very specific ranges. And what we know is happening as we put this energy through here is that electrons are jumping around inside the atoms of hydrogen, and they're producing very specific quanta of light that we're not getting out all sorts of the whole broad spectrum of light. These other colors in between here would just be some sort of interference. What we can see if we look at this through a prism is you have a band here that's kind of at purple, one at blue, one at teal, one at red. And if this was done in a classroom, it would look almost, I'm not going to say I did not take this picture, but I have seen pictures from my classroom, or when we've done this experiment in my classroom. It looks very much like this with the that interference in the background. If it is done under much more controlled settings, what you would see is something that looks much more like this. And I'm going to have you zero in. I'll come back to this slide in just a minute. But if we zero in on just the electron spectrum for hydrogen, what we can see is those same bands. So here's a purple, here's a blue, here's a teal, and here's a red. So this is obviously a stylized and a perfect magic chemistry land kind of version of what was happening in hydrogen. But what this is telling us is something very specific about how atoms work, and very specifically about how energy works when it interacts with an atom. And what we know can happen is that as a photon of light, okay, a photon of energy, in this case, that would be the electricity that was given to the sample, comes in, and it hits an electron. Here's our nucleus, and here's an electron. This one happens to be on principal energy level 2 here. Okay, so its energy is this electron absorbs an energy, a specific amount of energy. It can jump up to a higher principal energy level, right? So it goes from 2 to 3. And then after a certain amount of time, it will emit that. It will release that energy. It will fall back down to its ground state. We would call this the excited state for the electron. Jumps up here to the excited state, hangs out here for a little while, and then when it falls back down to its ground state, it would release the same amount of energy that it absorbed. Okay, and so what we see here is that there's not, that there are very distinct amounts of energy that hydrogen absorbs. Because it only releases specific distinct amounts of energy. It releases, at least within the visible range, the visible spectrum of energy, it only releases these 4 bands of light, which would correspond to what we would a lot of experimentation has found is jumping between some very specific energy levels. Turns out that the distance in or the difference in energy between principal energy level 1 and everything else is such a great amount of energy that it releases ultraviolet light when that electron falls back to the ground state in principal energy level 1. When electrons from the second principal energy jump up and fall back down, they have this is where they release the visible monolight. Hey, look, we have 4 different bands here that would correspond to the 4 bands that are right here. And then we know that electrons could jump back and forth between other energy levels, and this could continue going on forever. Now, I hear some of you out there saying, well, we know hydrogen only has 1 electron, so isn't that 1 electron always in the first principal energy level? We would typically say, we went back to electron configurations from last week, we'd say it was 1s1. We'd say that if we drew a Bohr model, we'd put it here. So this is what's happening here, is that electrons are absorbing more and more energy, or more, multiple atoms of hydrogen are absorbing energy that take it up here and then come up here, and then they're falling back down in predictable ways. And so to get up here, it might absorb some energy. To get up here, it would absorb a little bit more energy. It would release this, and then it would release this. And because in a sample of hydrogen that's as big as we have a huge number of atoms of hydrogen, we're going to see all of these things happening, right? So this 1 electron that's happening here would be releasing energy every time that it fell from any of these different places. I like to give my students the analogy of like stairs in the school, and we're a school that is 5 or 6 stories tall, and so I can jump from the first step to the second step. I can jump from the first step to the third step or to the fourth step. I can't jump directly from the first step to the 7th step, but the 7th step is still there, right? And if I had a couple of extra, if I did 2 or 3 jumps, I could probably get there. And a similar analogy would be at play for electrons. Hydrogen typically only has filled energy levels that are at the lower levels, but when we give it extra energy, those energy levels are still there and can be briefly occupied by electrons at the excited state. And so then we go back to this picture from before, where we have hydrogen right here in the middle with our 4 bands. Sodium has more bands, calcium. So, and as our atoms get much more and more complicated, they have more energy levels, they have more electrons. They're going to be jumping out all over the place. We're going to see some that match up, but we're not going to see electrons that or bands that match up precisely every single time. But what we see time and time again in all of these diagrams is that the energy is released in very discrete amounts of energy. And that we don't have just a full spectrum that says the electrons can jump up any amount and jump down any amount. We see, there's a big hole that's right here that says, at least for these 4, there's not an energy level that's being filled at that level. So these diagrams they seem pretty simple with just a couple of bands in it, but the understanding of the chemistry behind them is pretty complex, and kind of a cool thing. Helps us both to understand how the atoms work. It tells us actually why, like a Bohr model in some cases is a nice model. If we think that electrons travel around the nucleus like the planets travel around the sun, well, no, we know that that doesn't happen. But if we want to be aware of the distinct amounts of energy that electrons have as they're going out on these energy levels around the nucleus, that this helps us to understand those distinct energy levels. Those are not places in space, but they are energy levels that I think are cool and a nice part of, or nice understanding that comes from the Bohr model. Here's the entire electromagnetic spectrum. I imagine that this is something that you have seen multiple times in other places. We know that the spectrum is a range all the way from wavelengths that are very, very small. So our peaks would be very, very close to each other over here, to wavelengths that are very, very long, 10 to the third. So here's 1,000 meters between the crests, or the peaks, or the crests. We know that increasing wavelength, so the distance between the waves is longer on this side. There's a greater frequency over here, so more waves are hitting when the waves are closer to one another, and that over here we would have more energy. The waves would have more energy, right? So this is typically what we call gamma rays, X-rays, ultraviolet rays. And you can read this to yourself, but just understanding how these are all connected to one another is something that would be great for you to have. This infrared. I always connect the infrared with red light and ultraviolet with violet light. I think most students have that down, but a nice little trick there. Okay, the learning that the College Board identified for us in this topic was how the difference in absorption or emissions of photons in molecules will relate to the type of motion. And so I want to jump over real quick and encourage you to do this again. We've used this these simulations a number of times where we look at the PhET from the University of PHET from University of Colorado. I think there's some really, really interesting things, and you could spend an hour just playing around with this and get some really good learning on it. And so what I'm doing is we can select different molecules over here, but I'm going to just look at carbon monoxide, and we're going to imagine what it's like if we bombard this carbon monoxide with microwaves. Okay, and we know that microwaves don't always behave as, don't have those little balls like that, but it's a little bit easier for us to see how they interact. You can even slow this down. Did you see what just happened there? That one absorbed a microwave, and what's it making it do? Oh, that molecule is now spinning around. It's rotating. The other microwave's just kind of going past it. Okay, I'll hold this down until it emits. So it absorbed a microwave, it then emits it, and it stops rotating until we grab on to another one, and then it can rotate and rotate again until it emits it. Okay, let's see what happens when we instead bombard this with infrared waves. Oh, so a similar thing is happening in that it is absorbing and releasing this amount of energy. Okay, but the type of motion that's possible here is different. Now this molecule is vibrating instead of rotating. I'll wait for one more to do it. There we go. We got some vibration happening there. Okay, which is a super interesting thing to see. I'm going to turn this off before I change my amount of energy. We can look at visible light. Okay, there was one infrared particle that was left, or infrared wave that was left there. That's where that last one was shaken. But we see visible light is not causing either rotation or vibration, and ultraviolet is similarly not doing, or not rotating or vibrating this molecule. Okay, but I jump down to water. Let's turn this off just for a minute. We're going to go back to microwaves. Okay, we're going to change our water molecule. We're going to bombard this with microwaves and see what happens. Oh, look, that looks very similar to what happened to carbon dioxide or carbon monoxide, right? So we're going to see that this rotational motion is happening here. What would I predict might happen with infrared? Based on what we saw with carbon dioxide, I might predict that infrared is going to cause some vibrational motion again, and that's what we see happening here. Okay, visible and ultraviolet light are not doing anything similar. Now, because we have just a second here to analyze this a little bit more, I'm going to pull up nitrogen and go back to our microwaves. And what we saw happening with microwaves and carbon monoxide was some rotational motion was happening, that these microwaves are causing the molecules to spin around or to rotate in predictable ways. And that's not happening for nitrogen. And interestingly, would not happen for oxygen as well. So thinking about a difference between carbon monoxide here. So carbon monoxide and water are both spinning around in a microwave, but nitrogen and oxygen are not. So it'd be great to think about what's a difference between the molecules of what's similar about carbon dioxide and water versus what's happening with oxygen and nitrogen. Let's just for fun, let's look at infrared as well. We see a similar thing happening, no changes, but carbon monoxide is vibrating and water is vibrating as well. Okay, and the answer here is that we know that nitrogen and oxygen are nonpolar molecules, and so they're not affected by these waves in the same way as carbon dioxide and carbon monoxide, or sorry, water and carbon monoxide are, because water and carbon monoxide are both polar molecules. Okay, so the learning here that microwaves are causing transitions on rotational levels. That's what we just saw in those molecules. Infrared radiation is causing transitions on vibrational levels, and that ultraviolet and visible radiation are causing electron energy levels that we were not able to detect, at least in that simulation, but would still be happening. So we would connect. These are the let's go back. Excuse me, just for 1 second. Okay. So infrared and microwaves as compared to ultraviolet rays. So when we get to those ultraviolet rays, these are the higher energy rays. They're going to dig deeper down into the electrons instead of rotating or vibrating an entire molecule. Okay, so this would be a great opportunity for you to stop and go into PhET and play around with that activity. That one is called molecules and light. We're going to look at another one in a couple of minutes. So feel free to pause and go into that, and we'll see you when you come back to join us in a couple of minutes. The photoelectric effect is going to help us, again, get a better understanding of the calculations behind some of the observations we just saw. So there was no quantitative data that we really looked at here up to this point, but we're going to talk about absorbed and emitted photons. What's the relationship between their quantities? And we have a couple of equations that we're going to want to take a look at. So we know that photon is absorbed by an atom or molecule. The energy is increased or decreased by the amount of energy equal to the photon, right? So that's kind of a common theme that we've seen in a couple of different ways over the course of these two different simulations that we did, either those pictures or the simulation. The wavelength of the electromagnetic wave is related to its frequency and the speed of light by the equation here. So this is an equation that's given to you on our equation sheet. So C, which is the speed of light, lambda, so this is not an upside down Y, this is the Greek letter L. This is the wavelength. So I'd like to think of wavelength and lambda go together. So then V is the frequency. And the energy of a photon, energy is related to the frequency of the electromagnetic spectrum through Planck's constant. So V is consistently frequency, so H is Planck's constant. Again, the speed of light and Planck's constant are two things that are given to you on the equation sheet, and we're going to see how we would use those. So here's a question that came from a sample set that I had. Diagram to the left represents the photoelectric effect for a metal. Okay, so this also kind of explains what the photoelectric effect is. Metal surface is exposed to light with increasing frequency, and what we would expect is increasing frequency and energy of photons, right? So as this energy gets greater and greater, increasing frequency, at a certain point, electrons will first start being emitted from that metal. There is a PhET simulation on it, but it wasn't working on my computer, so you can certainly go ahead and play with this, but I think this diagram does a nice job of explaining it as well. We've got energy coming in here. We have to get to a certain threshold amount of energy before we can emit electrons. For the sample that was given to us here, that threshold is 3.3 times 10 to the minus 19 joules. So we're asking, if this is the amount of energy, what's the frequency of light that's associated with that energy? We're going to look at our equation sheet. We have both of those equations here. We even have those equations spelled out in terms of what their meaning is. And so the uninteresting thing here is that we can just solve for the math. So we're going to say the energy is equal to Planck's constant times the frequency. So we have two of the values. We're looking for the frequency. So we're just going to rearrange our equation to say the frequency is equal to E over H. And we are left with a frequency that is in 4.99 times 10 to the 14th wave per second, right? So the units on this are inverse seconds. We divided this by joules times seconds. The units on Planck's constant here are sort of strange, so just take a note of that up here. But the joules would cancel each other out, so we're left with inverse seconds because the seconds were on the bottom, and we would expect frequency to have a number per second, right? We could take this a step farther and say, well, what is the color of this light? So if our frequency is 4.99 times 10 to the 14th, what color would that? So we need to correspond that. We'd have to be given, right? You wouldn't be expected to memorize this, but if you were given a chart like this that said, here's the wavelengths of light, what color is the light that has this frequency? We're going to use the speed of light. And what our frequency is, again, our wavelength is equal to C divided by V, and we get to something like 6 times 10 to the minus 7th. The tricky thing at this point would be to remember what our conversion between meters and nanometers are, because what we just got here in this, our answer, meters here would carry down. So we'd have meters. How do we convert from meters to nanometers? Well, we know that there are 10 to the 9th nanometers in a meter. And so 6.0 times 10 to the minus 7th meters is equal to 600 nanometers. And so we have orange light. Now let's get into Beer's law for a quick couple of minutes here. I'm going to zoom through this screen because I think we can do a little bit better job of explaining what Beer's law, the Beer-Lambert law, relates absorption of light by a solution to three variables, and we have that equation that's right there. You typically will not have to use this equation as much as you would have to interpret data for Beer's law kind of a lab. So I'm going to jump ahead to this next screen. We're going to look at the PhET for just a quick minute, and then I'll give you your homework, or we'll do a couple practice problems before I give you your homework. So here's our equation that talks about this idea of absorbance. So absorbance is a measurement of how much light. So here in this setup right here, we have our testing solution is right here. We're testing a solution of cobalt 2 chloride, and we want to know when a specific wavelength of light is shined through this this sample, how much of it is absorbed by the sample. So what this is saying is, in this particular experiment, with everything set up the way that it is, when a wavelength of light, when light with a wavelength of 549 nanometers is shined through the sample, how much is absorbed by the sample. So we're going to compare how much went in to how much came out, and in this case, it's 0.72. Okay, there's a constant that is related to every different solution. We don't typically use that as much. We look at one solution at a time, and so because that's constant, we just leave it alone. And B is always related to the length of the sample, and I'll show you how that might make a difference. And then C is concentration. And so what an experiment will typically do is we will leave this epsilon and B the same. We won't change what the solution is. We won't change the length of the solution. We'll use what's typically called a cuvette. Looks like a very small test tube when we put it into this detector. And because the length of this doesn't change, these two variables stay constant, and we can say that there is a direct relationship between the absorbance and the concentration. And that's how we set up an equation like this. So just for fun, for a quick minute, I've looked up, I guess on the PhET, we've got they call it Beer's Law here. We'll go to the same solution. We can look at multiple solutions that are here. Okay, I'm going to put my concentration all the way down at 0. I'll leave this as preset, but you could play around with what would happen if you changed the wavelength of light. They choose a wavelength of light that's optimal here. We have 100% of the light is transmitted, which means that 0 of it is absorbed. Okay, so transmittance and absorbance are inverses of one another. Because our equation looks at absorbance, we're going to keep it here. And I'm going to come down to the bottom over here, and I'm going to increase my concentration of cobalt-2 chloride in my cuvette. And what I should notice is that my absorbance, you can just see that the color of the solution is increasing. And we should see that the absorbance is increasing as well. Okay. And for this setup, we can actually get to an absorbance that's above 1.0. We'll leave it alone right there for a second. What we would notice if we increase the length of this, right, more of the solution, more of the light is absorbed because we have more solution here. And if we decrease the length of this, we would see that less of the light is absorbed, which seems to make sense because there's less particles in here that would be absorbing this light and preventing it from getting over to our detector that is over here. Now, it's important to note that as we're looking at all of these solutions here, okay, even if we had Kool-Aid mix or whatever, all of these have different colors. And this type of experiment is only for solutions that have a color. We cannot use this method of analysis on a sodium chloride solution or something that would be clear without having a color on it. Okay, so this is something that we could play around with. The kinds of questions that you might be asked to consider would look like this. So a student is trying to determine the number of moles of iron 3 in a solution. And so they add potassium thiocyanate to the solution. And they convert it to potassium thiocyanate. So they convert all of the stuff into the, iron thiocyanate, which is FeSCN. And this stuff has a dark red color. Okay, and so here's the key. What the student does is they make let's see, 1, 2, 3, 4, 5 solutions that have very known concentrations, right? So they've measured, they know exactly how much of each of these concentrations they put in here, and they measure the absorbance at 453 nanometers. So we looked at a different wavelength of light in that simulation. Here is one that they represented, or they determined was optimum, and we're able to see the linear relationship, right? We even have another data point on here. When there's no solution, we made sure that there is no absorbance, right? So if it was just plain water here, it would be our control. And so here's where we see this direct relationship between the absorbance and the concentration. And so the kinds of questions that we would want to ask is the absorbance of the unknown, right? So we have an unknown solution is 0.2. So what's the concentration of FeSCN at that point? And so this is just an exercise in reading the graph in order to answer that question. So we would see that here is absorbance of 0.2 where it meets our trend line. And we would read down and we would estimate that the concentration of FeSCN is 4.0 times 10 to the minus fifth. Okay, and then the second question is how many moles of Fe3 plus were present in the sample? So we know that moles is equal to molarity times liters of solution. So we're going to convert that milliliters into liters. And we're going to say that our moles of FeSCN is 5.0 times 10 to the minus sixth. And in this case, because our mole ratio is 1 to 1, right, we can say that that's equal. I didn't put in my conversion factor right here, but that might be a good idea to add that in, or just make a statement in here to say that that's equal to this, and then maybe write a sentence. We have a 1-to-1 relationship between FeSCN and Fe there. Another interesting question that I saw was to think about experimental error, right? So the student did a similar experiment and where they had some standards. So they knew what the concentrations of the solutions were, or at least they thought they did, hint, hint. And they got a graph that looks like this. And look, we have 4 data points that are really clearly on the line, and one of these seems like it's kind of off, right? And so the questions ask, like, what's a possible experimental error that could have caused this point to be so far off the line? Now, looking back, I'm going to go to here. We clearly have some estimation that's happening, and we have this is not perfect magic chemistry land over here. But when we look at this data, we've got 4 pieces of data and one that's pretty far off, and we'd want to think about what is a possible source of error that might make that happen. And it turns out that there was probably some distilled water that was left in the cuvette, that was left in our container in the middle. And let's try to explain why that would happen, or how the student was probably just cleaning it out and didn't dry it out completely afterwards. And so what would happen there is the student, let's call this 0.05 molar. The student thought they put 0.05 molar cobalt 2 chloride into the cuvette, but because when the water mixed with it, and because that is such a small container, a couple of drops of distilled water is really going to have an effect, and so it dropped the concentration right here, right? We increased the volume, we decreased the concentration, and dropped over there. So that's an interesting way to think about how we might be asked about experimental error in a lab. That's a pretty, that's a tough question to ask in a relatively simple setup. So just be practicing thinking about things like that as we're moving forward. So that brings us to the end. It was kind of a rush through a lot of big topics, and I apologize. I hope that you took some time to stop and think. Certainly go back and play with those FET simulations that we have there. Pull out your chemistry book and read through some of the explanation of all of these different topics, because there's a lot more to it that I was able to present just in 45 minutes for today. Your AP practice problems are here. The analysis or the explanation that's up at the top is very similar to everything that we've looked at in the past. So if it's cut off with my face up there, I apologize. But the questions are asking what's the cobalt 2 concentration, and then calculate moles and mass percent. So here's a good, this is clearly related to what we did today, but B and C are connected to lessons earlier on in the year. And then 2 questions to piggyback on that. What's the approximate energy of one photon of this light, if they gave you the wavelength and the frequency? And then can you tell me what the color of that light is as well? Okay, so just real quick, I'll give you a second to get a screenshot of this if you need to. A screenshot of this one if you need to. And then just say thank you for joining us again today. We have so much fun presenting these lessons to you, putting them together. Hope that they are useful for you. If you continue to have questions, check out apcentral.collegeboard.org. Check out the resources that we have below in the links, or check out this tiny URL. And please, please, please reach out to anybody you know who may have internet or device issues, and have them contact us at cb.org/tech. Thanks so much, guys. Have a great day. Be safe and enjoy chemistry. Have a good one.